With question 8, we're looking here at the ocean, which has been treated with a black body, and so it has emissivity 1. And we're being asked to calculate the intensity radiated by the oceans. Okay, in this case, we're going to use stuff from energy resources. We know that intensity is power over area, and we've got our Stefan-Boltzmann law, which we're going to combine together. Power is sigma A T to the 4. Intensity is power over area. We can get rid of the area term from our Stefan-Boltzmann law and left with sigma T to the 4. And then just putting the numbers in, 289 Kelvin gives us an intensity of 395, which is approximately 400, and that's exactly what you're being shown as to show. Again, you must put in your value here to show that that is approximately the same as 400. It's not enough to simply put in the value 400 there. We then are asked to explain why the radiation is returned. Well, we should be aware from our study of this unit that the oceans mostly emit infrared radiation. So there's actually a mark there for discussing the radiation emitted by the Earth and hence the oceans. Once it's emitted, it is absorbed and re-emitted by greenhouse gases. Okay, now actually in the mark scheme it does say you get a mark for naming the gases, so methane, CO2 would be good examples. But the key point here is not reflection, but re-emission of the gases. Obviously, the infrared radiation is re-emitted in all directions, which means that it must go back towards the ocean. Okay, so we're looking for a kind of stage process here. We give out infrared radiation. What happens to that radiation is absorbed and re-emitted, and then why it goes back down to the ocean. Okay, we're then asked, what I would say is a surprisingly simple calculation question, but it's worth looking at. Okay, we're asked if we have equilibrium, i.e. The temperature not changing, the energy, we need to know how much additional intensity is lost by the oceans. Well, for an equilibrium, the energy in is equal to the energy out, and therefore that means the intensity in is equal to the intensity out. What that means is the intensity of the radiation coming in must balance with the outgoing radiation. Well, the intensity going in is, well, we've got 330 being returned to the oceans, and then we've also got some radiation from the solar radiation, which is 170. So we've got a total of 330 plus 170, which is 500 watt per meter squared going in. In the previous question, we calculated some outgoing radiation, which was an intensity of approximately 400. Okay. Well, there must be something else lost to balance that 500 coming in. There must be 100 watt per meter squared getting lost by the Earth in some other way. And then we're asked to sort of suggest a mechanism by which this is lost. A couple of nice ones. It could be lost through evaporation of seawater. Okay, so we're not looking at radiation per se, we're looking at where that energy may have gone, and one sink of radiation, if you like, it would be the evaporation of the seawater. And another way would be the melting of the ice, for example, at the ice caps. Okay. So the idea here being that the Earth still loses this energy, but just not in the form of radiation. Well, where must that go? One way would be melting the ice caps or evaporation.